this is Himabindu, Assistant Professor in IARE College. So today in this video, I would like to explain about the designing of pushdown automata. So how to design the pushdown automata and what type of languages we are going to construct the pushdown automata, we will see. So what is meant by pushdown automata, where we are using this machine and what type of languages we are going to use for the construction of pushdown automata, we will discuss. So here pushdown automata is a way to implement the CFG. So CFG is nothing but context free grammar. In the same way we design the DFA. So previously in previous videos we discussed about the DFA, designing of DFA, deterministic finite automata. Like that here we can construct pushdown automata. So here for DFE design we are using the regular grammars. So like that, to design a PDA, pushdown automata, we require the grammar called CFG. So context free grammar. So these are the designs, missions or models we can construct with the grammars. So a DFA can remember a finite amount of information. So what is the difference? So here coming to the Chomsky hierarchy, so we have a 4 type of grammars. So in that one, regular grammars or type 0, which is a subset of context free grammars, and this context free grammar which is a subset of context sensitive grammars, and which is this context sensitive grammar which is a subset of recursive enumerable grammars. So or unrestricted grammar, we can unrestricted grammar. So these are the different type of grammars. So in this one, with these grammars, we can construct the machines. For this regular grammars, we can construct a DFE, deterministic finite automata. With the context-free grammars, we can design PDA, pushdown automata. And here we can construct linearly bound automata. Linearly bound automata. Context-sensitive grammars, we can construct a linearly bound automata. And coming to the unrestricted grammar, we can build the Turing machines. So we can construct the Turing machine. So here these are the different types of grammars in the formal languages. So here with these grammars we can construct the we can construct the machines. So these are all the different type of grammars, and with these grammars we can generate the models or machines. And here coming to the DFA, so deterministic finite automata, which is having one limitation. So what is that limitation? In the sense, a finite amount of information. So here it can remember. So DFA can remember a finite, a little amount of memory. So it can remember only a little amount of finite amount of memory it can remember. For the DFE. Coming to the PDA, it can remember infinite amount of information. So here this is a limited one. And coming to the PDA, pushdown automata, so it can require many amount of, so it can remember infinite amount of memory. And PDA is more powerful than finite automata. So here the PDA or finite automata, either it is a DFA or NFA or epsilon NFA. So these are all finite automata, different types of finite automata. So these are all more powerful than finite automata. So obviously it is remembering more infinite amount of memory for the PDA. So it is a powerful than a finite automata. So any language which can be acceptable by finite automata can also be acceptable by PDA. So what this diagram says, so this is the regular grammar, so which is a subset of context-free grammar. So that this is a subset of context-free grammar. So that with the context-free grammar we can also generate the regular grammars. And what it indicates, with this 2 grammars we can with this regular grammar also we can construct the PDA. So what is this mean by? So for the regular grammars or also we can construct the pushdown automata. But context free grammars we can't construct the finite automata. That is the difference. Why? Because the context free grammars which are having the subset of regular grammars. So finite state machine. So it is having the limited memory, but PDA has more memory. So what it indicates, so for the construction of finite automata, it is a finite amount of memory is required. For the construction of pushdown automata, it's require more memory. So how to design that more memory in the sense we are going to add the stack. So we are going to add, we can add the stack into a FSM. So finite state machine. So here, what is meant by stack? So why we are going for the stack? Why means the finite automata FSM, finite state machine. So for the finite state machine, generally we'll give the input, and in the this is the mission for FA. We can write it as FA, whether it is accept or reject. So the string what we have given as an input, which is going to be accepted by the pushdown automata, or accept or reject. So for coming to the pushdown automata, we require additional memory, so that we are going to include the stack here. So for the finite state mission, we are going to add the stack to the mission, that so that we can store the infinite amount of memory. And here the stack is filled with the stack symbols. So here what the symbols we are going to use in the stack, in the sense we have what are the inputs values we have, and we have to, based on the input string, we will going to be push the values into the stack. And after that we can accept or reject. This is previously what we have explained. So for FSM, the finite state mission, and here it is the entire pushdown automata construction. So this is the model for the PDA, pushdown automata. And here what are the stacks? So what is the mean by stack? Why we go for the stack? So why we go for them, in the sense we need a infinite amount of memory, so that we require additional memory to store the values, so that we are using the one of the data storage. One is a stack, and a stack is a way we arrange the elements on the top of the another. So here we have the first in first out, not first in last out. So here first we need to push the values into the stack, and then based on the top of the value we can push or pop operation is going to be happened on the stack. And what are the two operations performed for the stacks? So here we are simply not, we can push the values. So here we have the stack, and we need to empty that stack, then only this stack is going to be, then only this model is going to be accepted. So like that we need to construct the pushdown automata. So, and for the stack, what are the operations we are going to perform? So here we have two operations. One is a push operation and pop operation. So push operation is nothing but we are going to add the new element. So new element is going to be added into the top of the stack, and pop is going to be pop element on the stack, which is going to be eliminated or removed from the stack. That is also top. So top, whatever the symbol is there, we need to pop the top values only. So these are the two operations we are going to perform on the stack. So why we require the stack in the sense? So we need a infinite amount of memory for the pushdown automata, or for the context free grammars to design the pushdown automata. So that's why we are using the stack. So in that stack we can use we can store multiple values, so that we can construct the pushdown automata. And here, what is in PDA, we have some terminologies. What are the terminologies we are going to use to construct the pushdown automata? So, first one is the ID, instantaneous description. So, in this instantaneous description, we have a three tuple values. So, what are those in the sense? The Q, so which is the state. So, what is meant by state? So, presently, suppose here this is the state, this is the initial state, and this is the next state or accepted state. So that in this state, so this state is represented as a state, as a Q. And here W is the string unconsumed input. So whatever the, suppose here 0011 is there. So in this one, whatever the string is there, we need to represent in the IDs. Suppose here the delta of Q comma, so input string is 0011 and S is the start symbol. So how we are going to design in the design the PDA in the sense we require CFG. So context free grammar we require. So this context free grammar, we have context free grammar, we have the production rules. So here in the production rules, S tends to A or S tends to AB. Like this, we have the production rules. So here, based on the production rules, we are going to, whatever the start production rule is there, in that one, left hand side, what is the value we need to represent as a start symbol. And here this is the stack contains S. S means how many stacks. So here the stack values are there. We are representing those values with the S. Top of the stack symbol. And here turnstile notation. So what is meant by turnstile notation in the sense? It is used for connecting the pairs of IDs. Suppose here, let me write one ID, then I will write 0011, same example, and top of the stack symbol is initially will represent with the Z0. So Z0 is there, and here, so here after this one, after consuming 0 input, so 0 input, the turnstile move is transition of Q comma. So whenever the 0 is there, we need to push the value into the 0. So 0 we need to push in the sense, and top of the stack symbol is now 0. So here 0, remaining input symbols we need to write. And what we have done, so here 0 is there. While reading the 0 input symbol, we will push the value into the stack. So Z0 is there. And here turnstile move off. So here next 0 we need to read. And here Q and 0 is there, and so one input and one input. After reading this 0, so this 0 is going to be pushed. So that 0 Z0. So 0 is also pushed here. So here this turnstile notation. So this turnstile notation is a connecting the pairs of IDs. So here one pair, this is one ID and this is one ID. So we need to connect these pairs so with the turnstile notation. So what it represents? Turnstile star, which is a multiple moves in between the IDs, instantaneous description. So turnstile is represented with the fallen T, and it is one fallen T represent, it is moving from one. So one move is happened here. And here turnstile notation sign describes a sequence of moves. So here this is a sequence of moves. So this is about the turnstile notation fallen T. And here this is the example. So how we are going to represent. And these are the IDs. So here this is one ID and this is one ID. So in between, what are the, so here if you observe, so here this is the P is the current state and Q is the next state. So while consuming this input, so there may be in some examples there may be a state change. So here the state change, here current U is there, and next state is P is there. So we need to represent the values like this is the current state and this is the next state, and B is the input. So after reading this input, where the W is going to be replaced. So W is going to be replaced and A is the value. So A is the value whatever the top of the stack symbol is there after reading this B. So these are the terminologies for the pushdown automata. And here, these are the examples. We can construct the pushdown automata. With the examples, how to construct the pushdown automata, we will see. So here is one language. So language. So pushdown automata is having the language, context-free language. So this context-free language, why we go for context-free languages instead of regular grammars in the sense. So here it requires in suppose here this is the example a power n b power n. Why can't we write in the regular languages? Why? Because so in regular languages this a power n b power n is there. So here n number of a's followed by n number of b's. N number of b's. So here n number of a's followed by n number of b's. So in the regular grammars, we have this kind of examples, a power star and b power star. So this is going to be happened in the regular languages, but not in the, so the a power n and b power n, this is not a regular language. So why? Because here the absence of A or B, it is acceptable with the regular languages. But here absence of A or B, whatever the input symbol starts with A or B, so compulsory the condition in number of A's followed by n number of B's should be followed. So that's why this A power n and B power n, which is not a regular language. So this kind of languages will comes under the context-free languages. So this n number of A's followed by n number of B's. How to design the pushdown automata? So here the logic behind the construction of pushdown automata is we are using the stack symbol, stack. So in that one, we have to use the operations called push and pop operations. But after emptying, so here with the pop operations, so here it is the stack. Initially, we have to start with the Z0. And then whatever the input symbols are there, we need to pop, and according to the language, we need to pop the values. So here after popping, after completing the input string, we need to reach Z0. So we need to, whatever we are initializing the stack, to that state we need to come back. So after finishing all the input string. So whenever we are reaching the Z0, we are going to be accepted by the pushdown automata. So the string which is going to be input, string which is going to be accepted by this pushdown automata. So this is the logic. So here first we need to give the input symbol, then based on the language or grammar, we need to perform the operations called push and pop operations. So after that, after reading all the input string, whenever we are reaching the end of the stack symbol, that is Z0, we are going to be accepted by the pushdown automata. So let's take one example. We will discuss the designing of pushdown automata. So here is the language a power n and b power n, and the condition is n greater than or equal to 1. So here if you write the language, so a power n, so starts from 1. So first we need to write the minimum length, then we will write the maximum up to maximum. So a power n, so n I am taking as 1 and b as equal to 1. So n is equal to 2 and b is equal to 2. And here a power 3, b power 3 and so on. So in this one minimum length is a, b. So here, so if you observe the a, b is there. So here we require the stack here. Initially we'll write the Z0. And if you read A, we need to push the value into the stack. And if you read B, we need to pop the A value. So that why? Because we can count number of A's and number of B's. So here we require how many A's are there parallelly. We have to check for the number of B's. So how many B's we enter, how many A's we enter, we need to pop with the while reading the B value. That is the logic here we need to follow for the construction of pushdown automata. So here, so how to design this one? So we are going to construct the transition diagram. So here, what is the logic here? We need to start with the Q0. So here initially we need to initialize the value Z0, and here we'll take this value AABB. So here the string is AABB. So here, so while reading A, what is the logic we have? So while reading A, we need to push the value into the stack. So the pushing the value. So here we need to represent with the 3 values. So while reading A, and top of the stack symbol is now Z0. So and Z0 is there, and what we are going to do, this is the replacement value. So Z0. So initially what we input is here, this is the input, and top of the stack symbol, and here replacement value, and here for the 1A. So if you here n number of A's followed by n number of B's here. So n number of A's are going to be there in the input string. So for that one, we are going to be write like this. So for multiple A's. So this is the input, and A is there whenever the top of the stack symbol is already A, and we are placing one more A, so that we will write like this. So input is A and top of the stack symbol is A, and here what is the replacement? So what is the replacement? Here we are going to add the value into the stack, and here from this state, so here we finish the 2 A's here, and for B, so for reading the value B. So here for the input A, we are in the same state, and for input B, so we are going to move to the next state, that is a Q1 value. And here the B is the input, and now the top of the stack symbol is A. And what we have to do, we need to pop the values. So that popping, in the sense, we have to write like epsilon. So epsilon is nothing but the popping the top of the stack symbol. So here for reading B value, so for reading B, so we need to pop the top of the stack symbol, that is A. And here we have multiple B, one more B also. So for this one, so we need to write loop like B, and top of the stack symbol is A, and we need to pop one more A. So for this like multiple B's, this is the operation we need to perform. We need to write. And here finally, so after completing all the B's, we have the input symbol Z0. We have the top of the stack symbol is Z0, and after reading all the 4 values, we have the epsilon symbol. So from this state, epsilon symbol, and top of the stack symbol is now Z0, and what we have to do, we need to move to the final state. So that is the final state, or else we can replace that Z0 and we need to move to the final state. So this is how we are going to design the pushdown automata for the given context-free languages. So this is for A power n and B power n. So number of A's, n number of A's followed by n number of B's here. And we'll take one more example, A power n, B power n. So here one more condition, n greater than or n greater than m value. So here we'll write the language, then we will get the clarity what to do. So here a is there, a power n. So n greater than or equal to 1. So here we'll take 1 and b power, so b power also 1, and the value should be, n value should be greater than m. So that I am taking a2 and a power 3 and b power 1, and also we have a power 3 and b power 2. Why? Because so not only one will accept, b just condition is n greater than 3, so n greater than m. So n while taking we need to construct like this, and a power 4, so b power 2 and b power 1 and a power 4, b power 2 and a power 4, b power 3. So these are all the possibilities of languages. So that, so here these are all the possibilities of languages. So here the number minimum length is, number of A's is AA, B is accepted here. So here AA, B. So for this one, so while designing the pushdown automata, we have the option first. Initially, we need to start with the Z0. Then, so here A is there. So while reading A, we need to push the value into the stack. And while reading B, we need to pop the value of B. And whatever the extra A's appear, we need to pop, or we need not to do anything. We need just leave and go to the final state. That is going to be happen for the construction of this kind of languages. How we will design. So initially we have to start with the Q0, and so here we will take, so A as an input. So pop or push operation. So while starting, Z0 is there and we need to push the value, and also we have the value A. Top of the stack symbol is again A, and we need to push the value into the stack. And here whenever B appears, so B appears, we need to pop the value. So we need to pop the value, and so that B, how many B's are there, we need to pop all the A's. And also when we reach, so this is the state. So after popping all the A's, so again we have the value from the Q1 state, again we have the value A is there and epsilon is there after reading all the values. So epsilon empty string is there, and top of the stack symbol is A is there, and top of the stack symbol is A, and we need to do A as it is like this, and we need to reach the final state. So this is for extra A's, and whenever we reach, so over the top of the stack symbol after reading all the A's, we reach the Z0 and we need to move to the final state, that is with the Z0, Q, F. So this is about the A power n and B power n. This is for extra A's. We need not to do anything. So whenever we reach, we don't need to anything. We have to just leave the number of A's, and we need to go for the epsilons. We need to go for the initial state, initial stack of the symbol. Then it is reaching the final state. So these are the two examples with the A power n and B power n, and A power n and B power n. And coming to the another example, here is the condition, number of A's followed by number of two times of B's. So here writing the language, so here n is greater than or equal to 1. So we will write the language. So n from starting, n is equal to 1, and B is equal B power 2 power 1, and A is equal to, n is equal to 2, and B power 2, 2. So and so on. So here A power B, and AA 2 to 4, B, B. So number of A's. So how many A's are there? How many B's are there? So here for one A, we are going to have for the two B's. So what it indicates? So while push and pop operations, so initially, so for one A is there, we have to pop the two values. So here, what is the condition behind? So while reading A value, we need to push the values two times, so that so it is equalizing to A power 2n and B power 2n. So how it is going to equal in the sense, so number of A's is followed by number of B's. To equalize these two things, we are doubling the A value here. Why? Because only single value is there. So here we need to double the A value. So that's why while reading A value, input string A value is there, we need to push the two values, two A's into the stack. Then while reading B's, how many B's are there? We can pop the values like this, so that we can construct the pushdown automata. So for this condition, we will construct. So initially we have to start with the Q0, and here while reading A, so top of the stack symbol is initially Z0 is there, and what we have to do, we need to push the values, two A's into the stack. And for the second A, so A is there and the top of the stack symbol is A is there, and what we have to do, we need to push two A's into the stack. And for B input, and the top of the stack symbol is A, and what we have to do, we need to pop. So here we'll take this ABB string, and here what we have done, so let me derive this string, then you will get the clarity. So initially it is a Z0. So while reading A value, so A is there, what we have to do, we need to push the two A's into the stack, and while reading B, we need to pop the A value, top of the stack symbol value A with the operation epsilon. And here, so this is the next state. And here one more is there, one more A is there, and we have the value B, one more B is there. So B, while reading B, we need to pop the values. So for this, already we consumed one B. So for multiple B's, we need to write like this, A comma epsilon. And here we reached the value Z0. So this is for epsilon. So while reading the epsilon symbol, and we have the top of the stack symbol is Z0, we need to do Z0 and we need to push that. So this is the finite state. So this is how we are going to construct the pushdown automata for the A power n and B power 2n. So till now we have seen only two values, so A is followed by B, and now we will introduce one more input symbol, that is the C here. So here also some conditions. A, we have two types of values here. So A, B or belongs to same power, and B, C is not belongs to the same power. So for this one, how to design this kind of pushdown or language with the pushdown automata, we will write. So first, so logic we need to tell first. So here initially it is a Z0, and A power n and B power n, we need to divide like this, A power n and B power n, and which is followed by C power n. So here A power n, B power n, we already discussed how to design. So this is the A power n and B power n. So what the logic is, whenever we are reading the A value, we need to push the A values into the stack, and whenever we are reading the B value, we need to pop the A values into the stack. So this is AB. So and after this one, we have one more value, M is there. So M is there. So M, C power M. So how many C's are there? We need to just go to the final state. So that is the logic we need to write. So A, when reading A, we need to input the push the values into the stack, and while reading the B, and we need to pop the values. So while reading the C, so we don't need anything. We do not do anything. So simply it is having the top of the stack symbol is Z0, and C is the input symbol, and top of the stack symbol is Z0. We need to only do the Z0. So just top of the stack symbol is we are not going to replace that value. So this is the, and how many C's are there? We need to repeat the same step. Z0. So here, for these conditions, how to design the value. So initially we need to start with the Q0, and what is the logic behind this one? A power n and B power n. So how many A's are there? So we need to push the values into the stack, that is A. So for this is for multiple A's. So how many A's are there? We need to, and this one is for B input. So while changing the input, we need to move to the next state, that is a Q1, and top of the stack symbol is A, and we need to do the epsilon operation. So this is for one input symbol, one B, and two more B's, A epsilon. So this is the operation all performed. So A is followed by B is finished, and we need to follow for the C power m. So how to design this one? So after finishing all this one, we have the input symbol C. From the Q1 state, C is the input symbol and top of the stack symbol. So why? Because only Z0 is there, in the sense we already popped all the A's into the stack. So while reading B's, so number of A's followed by number of B's. So how many A's are there? Must and B's should be in n number of B's only. So that A is popped, and A is popped. The only thing is Z0 is there. So that's why the top of the stack symbol is Z0, and we don't need to do anything while reading the C input symbol. Simply we need to reach the final state. So that is the QF is the final state. So this is for one C, and for multiple C's, so C, so top of the stack symbol is always C Z0, and we need to do the nothing. So while reaching, it is after reading the C input symbol, we need to be there in the final state. And this is, so for this example, we just will change the m and n values. So A power n and B power m and C power n. So for this one, same constraints. So here for this one, so here number of A's followed by number of C's. So same thing, we need to replace, we need to do thing while reading the C value, we need to pop the A values. And here, whenever we are having the B value, we need to do nothing. So how to design this one, we'll see. So this is Q0, which is initial state, and A is there. So A, for A input, A Z0, and multiple A's, we have to push the values. And here for the B, so here a number of A's, how many A's are there, we need to push the values into the stack, and number of B's is there, B. So here the top of the stack symbol is A, and what we have to do, we don't need to do anything. So why? Because here B is there, but if you do anything, if you push the values, again we don't have to don't have to chance to pop the values of B. So that's why we need to do, we don't need to do anything. So that is, whenever while reading the B value, we just do nothing, we'll just stay in the same stack. So this is for one input, and if you have multiple B's, we need to write like this. And here from this state, Q1 state, so we have the C input values. So C is there, C is the top, C is the input value, and now the top of the stack symbol is suppose here Z0, and A is there, and here for the same top of the stack symbol is A, and A power n is followed by C power n. So while reading C, we need to pop the A value. So here A popping in the sense we need to write like this. And this is the Q2. And for the C, multiple C's, we need to write multiple C's. So CC is there. Suppose here A power A power AA and B CC. So this is the input string. So AA we just push the values and B is there just read BB is the will, right? So we just done nothing. And while reading C, we just popped first A, and while reading the C, second C, we need to pop the one more A. So that is and after this one, we have the string empty. So for empty string, empty, and top of the stack symbol is Z0, we have to move into the final state, that is QF. So this is A power n and B power n. So with the three input symbols. So three input symbols A, B, C. So this is one type and this is one and this is one type and this is second type. So we'll just replacing the values. Suppose here A power m, B power n and C power n is there. We need to equalize this. How in the sense? So we need to push the B values into the stack and pop while reading the C values. And then while reading the A value, we don't need to do anything. So this one about these two examples. And here we have the example like A power n, B power. So addition is there. So here how to design this one. So here language which tells so A power n, B power m plus n, C power m. So here this B will write it as a m, B power n. So what it indicates? B power of plus will write. So in mathematics we can do like this. So here if you observe there is a pattern, n number of A's followed by n number of B's and n number of B's followed by n number of C's. So that I will write it as A power n and B power n, B power m, C power m. So these are the two different things. So here while reading the values, so here while reading A input, we need to push the A values into the stack, and while reading B, we need to pop the values of A into the stack. Suppose here Z0 is there. So for reading this A, so we'll write A, and while reading B, so we need to pop these two B's, and again we have the value B. So that how we have to do, we need to push the values of B, and then while reading the C, we need to pop the B values. So that it is reaching again the top of the stack symbol is Z0, so it is accepted by the push PD A. So for this logic, we need to construct the transition diagram. So A power n, B power n as usual, we will start with the Q0. So whenever A is there and top of the stack symbol is Z0, and we need to push the value into the stack, that is A Z0. And also one more input, A, for double A's or multiple A's, we need to push the values of A into the stack. And here we have the input value change B, and top of the stack symbol is A. And we need to perform the pop operation. For multiple B's, we need to do like this only. And here from the Q1 state only, we have one more B power m is there. So for this one, we need to write like this. Same B and top of the stack symbol. After popping all A's, we'll reach the Z0. So Z0 and while reading B, after finishing B power n, we need to push the values of B power m. So B power m, B, Z0, and for multiple B's, we need to write like this, B, B. And here, after this one, we have the input C. So for C input, we need to go for the another state, that is a Q2. And next C input is there, and top of the stack symbol is now B. So B is there, and what we have to do, we need to do pop operation. For this is for single C, and if we have multiple C's, so C, this is going to be in the self state for the all inputs. And here finally we have the input symbol epsilon. After reading all the values, we'll get the epsilon. Then for the epsilon symbol, and after popping all the values, we have the input symbol Z0. Sorry, top of the stack symbol is Z0, and we need to do nothing. So simply go for the final state, that is QF. So this is about the construction of A power n and B power m plus 1. So plus is there, we need to we need to do like this. So concatenate operation. So then we'll design the pushdown automata for this kind of examples. And here the replacement of m plus 1 is changed here. So previously for B we written like that. For C, so same how to design this one, A power n and B power m. So C power n I am going to be write like this. So here we'll match the values though that. So here these two are same, and A power n, B power, C power n. So same logic, what we have to do, we need to, while reading the A values, we need to push the values into the stack, and while reading C value, we need to pop the values of A. And while reading B value, we need to push the values into the stack. And while reading M value, we need to, while reading the C value, we need to pop the values of B. So how to design this one? This is the Q0. So while reading A value, so A and top of the stack symbol is Z0 and A Z0. And for multiple A's, we have A. And here, after reading the values of B, so B, we need to go for the B also. So we need to write top of the stack symbol is A, and we need to push the values into the stack. And here a Q1, and so B is there, and for multiple B's we need to write like this. So B and A. So not like this. From this same state we need to write like this. So here, so B, top of the stack symbol is Z0, and we need to write like B Z0, and B. And from this state C, so C, while reading the C value, we need to pop. So here for C power m and C power n is there. So how many A's are there, how many B's are there, we need to push the values into the stack. So but for the matching, while reading the C values, we need to pop. So while reading the C value, and top of the stack symbol is A, and we need to do epsilon. And while reading the C value, and B is the top of the stack symbol, we need to pop the values. And this is going to state change. So this is for multiple state, C, B, epsilon, and C, A, epsilon. And here after finishing all the input string, we reached the empty string, and for the top of the stack symbol is Z0, and we need to replace it with the Z0 only, and we need to go for the final state, that is QF. So these are the examples of finite state, examples of pushdown automata. So how to design this kind of context-free languages, how to design the pushdown automata, we have seen in this video. So these are the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.